standoff, and this is last day of standoff that starts with a presentation from representative of Microsoft. It's called Windows 10 Hardware Security Mechanisms, and it is presented by Mr. Artem Sinitsyn. Good day. Thank you very much, dear organizers, for taking interest in a topic that is really relevant, this being hardware security of the most popular OS out there, Windows. I'm CISSP, CSSP, and MCSE Security Program Manager for Central and Eastern Europe. And in the nearest 50 minutes, we're going to learn why we need hardware-backed security, and it's not enough to use software-based security methods. We're going to look at what virtual-based security, VBS and VSM, means. I'm going to give you additional information about each of those. If time allows, we're going to go quite deep into various technical aspects of technologies. We're also going to look at various means to protect Windows 10 systems that are called guardians or XXX guards. We'll look at credentials guard, systems guard. We're going to look at ways to seeing to it that integrity is seen in the kernel, how to prevent direct access to the memory, kernel DMA protection. We'll look at the differences with secure boot. We'll look at why it is so important to vendors and OS manufacturers to work together hand in hand with processor manufacturers to have in place things like SMM protection. And we're also going to look into secured core PC. Is it something that you can make with your own hands, or you need it to be pre-installed and pre-tuned, pre-configured for you? So, a lot of content ahead of us, so let us get going. Like I said, all the most important components of Windows 10, security components, are called guardians. It refers us to a particular type of attacks or particular category of goals of attack. So it's something and then guard. Not all of them use hardware security mechanisms, but 90% of those use hardware-based security mechanisms. We're going to discuss hybrid approach today that is tied to hardware mechanisms from equipment vendors. For us to understand why it is impossible to just go with software security mechanisms to secure our workspaces, I'd like to demonstrate to you an architectural issue that has to do with local security authority subsystem. So what LSAS is something that you clearly understand, but let me remind you. Components of LSS are in charge of secure storing of credentials, accounts, services, and the like, and they also participate in authentication, user authentication procedure, as well as other user and system processes in the OS. Most of you most probably know the screen that you just saw in the slide. It's Mimikatz utility that you all know. And just to demonstrate it to you, let me demonstrate to you the tool that is a whole category of attacks or attack scenarios aimed at stealing credentials from Windows OS. Mimikatz allows to steal credentials or something like that that is in LSS. In the photo on the right, it's on your right, right? Yes. It's Benjamin Talbot the author of Mimikatz. It's thanks to him the attackers and guardians alike have this wonderful tool in their hands. And now let us switch over to demonstration of Microsoft Whiteboard. I'll use Microsoft Whiteboard rather than demos. Am I back? That's bizarre. Looks like Zoom switches off my video cam. Can you hear me? Yes, we can still hear you. Oh, okay. Okay, so you can still hear me, you can still see the whiteboard. So, let me show you this. You all know that we have two main levels in our operating system, the kernel mode and the user mode, right? So, in user mode, Windows OS has processes that consist of a program and a library of programs that are sometimes downloaded dynamically. In kernel mode, we have things like data structures, things that describe operation and limitations associated with the way user applications are operated. For example, if user application needs access to a memory address or an object in a file system, then by going into other data structures in kernel mode, you still get what you want, right? So keep that in mind. Right. Now let us discuss how software security mechanism works. In data structure, there are ACLs. The ACLs are there to describe authority of processes launched in the user mode. So, thanks to this mechanism, what we have in place is the so-called logical isolation or program-based isolation. I'm a bit annoyed that my video keeps disappearing. Can you see my screen now? Great. Okay. So, all is great, but let us imagine that rather than speaking of something abstract, we're speaking of something really critically important for Windows operating system normal functioning. Something that has to do with LSAS that is aimed by Mimikatz and the rest of the utilities like that. Please write to me in the chat, which is the mode in which LSAS works. Is it UM or KM? Turns out it's not a trivial question, and oftentimes users interpret it erroneously. They don't have correct understanding of LSAS architecture. Ivan, can we check whether somebody responds in the chat to the question that I posed? Yes, there you go. Half and half, 50-50. Yes, right. So 50% of our users believe that Mimikatz and LSAS works in kernel mode, and the rest that in user mode. Probably it's not that obvious, but it does work in user mode. LSAS works in user mode. And this is indeed the source of problem to protect against Mimikatz. Let's add a malware like Mimikatz. An adversary, and for Mimikatz to work, for its main functional to work, we need to have administrator privileges to attach debugger to any process in the system, right? So Debugger gets us access to the memory, and then you dump any kind of information, any data that's situated in the memory of this particular process. Let me switch off all the reminders so they don't distract us. So, problem is that if adversary is right here in the kernel mode, it has access to data structures that are in charge of all the processes in user mode, including LSAS process, which means that it has access to what? Right, to ACL. It controls the mode of security with which LSAS is going to be launched. Since Windows 8, we have this thing called PPL, Protected Process Life. It's like a semaphore flag that can be used in kernel mode, and it means that if a process has PPL flag, then nobody can attach a debugger to it. So if we're talking about LSS, then Mimikatz cannot execute. So it's great. No, it's not. Let me remind you that if you have access at the kernel mode level, you can just switch this flag off. And those of you who know syntaxes of Mimikatz utility, it's something like contact process disable. So the moment you have administrator rights, you can actually remove the flag. That's why software LSAS security is not effective and it's not good enough. Adversary just has to execute one additional string. That's it. I mean, this is a big if, and you have to be masterful to develop this attack and to get those credentials. So you have to be a reasonably proficient adversary to do that. So what to do with it? Oh, and before I forget, let me switch the whiteboard off and get back to... No, we don't have to return back to the slides. Let's keep talking about how this security system is realized and how it's done in Windows OS. Let us wipe it off. I really need to see to it that I have enough time to tell you all the very interesting stuff. Slides are going to be available to you anyway, so please feel free to use them as a reference point later if I do fail to tell you something. So, okay, now we know that it's ineffective to work just with software security methods, and administrator rights allow to bypass any security mechanism, software security mechanism. Adversary can do that. So how processes are isolated in user mode? I mean, how processes are isolated from each other in user mode? Isolation is rather straightforward, but not too straightforward. Let me explain myself. You have a range of addresses dedicated in the virtual memory for these particular processes, for process 1 and process 2. So let's say this address is 13,000, and this one also 13,000, but through virtual address, the physical addresses could be quite different, 9,000 and 11,000. So we have an abstraction level, and this translation is controlled by NTOS. All is great, so we can handle logical isolation of processes from each other. Effective isolation in user mode from code or from adversary that has kernel mode access is impossible to realize, right? We already know that, because when controlling kernel mode, it controls all the probable mechanisms to provide security in the system. Now, let us imagine that this is a virtual machine, VM1, and there is another virtual machine VM2 was same OS system launched there with user mode and kernel mode. So processes that work in this OS also address particular set of addresses. In this level, this would be guest virtual addresses, GVAs. Here also guest virtual addresses. They get translated into guest physical addresses and then into system physical addresses. So this part, guest physical and system physical addresses, translation of second level, is realized through SLAT. Hypervisors do not operate without SLAT. So in order for you to launch Hyper-V from Microsoft, you really need SLAT support. I'm simplifying, but this is what it is. So why do we need SLAT? Let me explain you why. What if, rather than talking about virtual machines and OSs, we're talking about smallish containers? Small containers, let me start. And I'm wiping it off, and what I'm drawing right now, what I'm going to draw right now, is to explain to you what is virtualization-based security. It's a hybrid approach when we use both software and hardware security mechanisms to isolate the critically important processes that run in the OS from potentially dangerous or potentially malicious processes. VBS is virtualization-based security, and it allows us to realize virtualization security mode. It's a safe architecture based on virtualization. So in VSM, apart from having our standard user mode and kernel mode and the rest, we also have a new context, a new security context created thanks to the isolation. We have IUM, isolated user mode, and we have SKM, secure kernel mode, not isolated, secure kernel mode. So here we have our LSAS, right? Here we have our NTOS. It's like kernel of our operating system. And here we have SK, secure kernel. So now, so what we do next, from LSAS, we take the credentials, the most secretive data, derived credentials as we call it, and we put it into the isolated version of LSA. It would be called LSA ISO in Task Manager. It's an isolated instance of LSA security that is realized in isolated user mode by way of using hardware and software technology, VBS, virtualization-based security. So now we drag the data from here to here, while authentication procedures and managing requests coming from various SSP pack, security service providers that realize NTLM or Kerberos or other security processes, all that is realized on the left from the standard LSA. The data stored on the right, and they do not leave this container. And our adversary, we're looking at the same scenario, it's right here. Why is it yellow? I wonder. Let me change that. So this is our adversary who still controls kernel level of the OS, and it can launch Mimikatz. Even when it controls LSS processes, it can't dump data from here. For one particular reason, the data are in the isolated process, LSA ISO. And the process interacts through the so-called SBUF, security buffer. So what is security buffer? It's a structure, a bus, or a proxy interface controlled by hypervisor. That is to say, on hardware level, Hyper-V, right? So when these processes, LSA and ISO LSA, interact with each other, they are fully controlled. The data exchange is fully controlled by security buffer. For better understanding what it is, well, you probably exchanged currency at one point, right? So the teller would provide you with a tray, and it's a smallish tray. And it is covered with bulletproof glass. So you put something into this smallish drawer or tray. The teller takes this tray and drags it to himself. So it's a fully controlled process, controlled by the teller, right? If the tray is not provided to you, then you cannot give the teller the money to exchange your currency. So you request something, but communication through the bulletproof window and through the tray is fully controlled by the teller. So this is what secure buffer is all about. And to extend this analogy and to illustrate to you that this is truly secure, we need to go further. Our S buffer is our tray, right? Here it is. But in actual, but there is no process behind those buffer, but behind those buffer. You communicate with the teller through this tray. If you do break the glass, the bulletproof glass, you get access to the teller and to the money that the teller handles. But in case of secure kernel Windows 10, in virtual secure mode, this doesn't happen because there is no teller behind the bulletproof glass. Thanks to marshalling, what we have on the other side of the glass is a portal where you would just send a request from standard portal LSS. It would go to the isolated instance of LSA ISO, and then you get answer from that port. So to get open data from there is unreal. You either have to compromise the whole procedure of creating a virtualized container, or compromise the Hyper-V to change the limitations to access to the memory segments that are dedicated to critical services like LSA ISO. So, sorry, I incorrectly illustrated it. LSA talks to a secure kernel, and then it goes to LSA SAS. Like that, yeah. So, the attack surface is minimized, all challenges identified. You can't change any parameter. And you cannot ask the LSA ISO to send you open data, to dump this data and compromise it. And all these processes work in RPC. A very abridged version of RPC that only supports a limited list of system calls. Right, now, and also for us to understand this thing, launching in this mode is called credentials. guard. It's just a name. What we have under the hood, however, is launching an isolated instance of LSA subsystem that stores the credentials and other systems secrets that is launched in a separated, virtualized and isolated container thanks to VBS technology. Right, okay. So how can an adversary develop this attack? Because adversaries are not fools, right? And actually Mimikatz has the corresponding function to bypass what I've been drawing quite nicely. So let's look at the trick used by the adversaries. We have our isolated user mode, our secure kernel mode, our regular kernel mode, and our regular user mode. Oh, and one other thing I forgot to mention. From the point of view of Intel architecture, just for us to understand the trust level and how the landscape and attack surface changes when using this approach, we need to understand that OS kernel works right on top of the hardware, but it does have Hyper-V in between. Between the kernel and the hardware, there is this inner layer of Hyper-V. And then we have all these things like CPU, memory, all kind of devices. And we do remember, I think, that in Intel architecture, this one is R3, this one is R0, hypervisor Hyper-V is -1, and since we also add vertical distribution in terms of trust to the code executed, we also extend it horizontally so that inside the OS, we could isolate something really critical in the OS by way of using hardware isolation. So now we also have virtual trust level 0 and virtual trust level 1. VTL 1 is more trusted than VTL 0. This is the container that houses credential guards and other critical services that we're going to talk about later. So what adversary can do? It still has control over kernel mode security systems and also administrator rights. So he can escalate privileges the way he wants. Now, access here into LSA ISO is something that adversary cannot get because he cannot. Here is our secure kernel. Here's our secure buffer and our regular LSA SAS. He can dump LSA, regular LSA. He can, but he only gets something not usable. It's just an encrypted block of data, and you can't do anything about it. But our adversary is smart, and he knows that if he cannot gain access to data from here, because it's blocked, he can still hijack data while the data is introduced into an element of user interface, right? In order to do that, the adversary may want to drop a driver here, maybe DLA or something from the library, launch it in kernel mode and use it as an implant. And the point of time when the user in the user interface is going to introduce data, before this data are put into LSA ISO, at that point of time, he can hijack this data. While they're going into the isolated user mode, they could be theoretically hijacked. And if they are even encrypted, they can still be restored. If you have worked with Mimikatz and its related tools, if you have administrator right and kernel mode access, you can register your driver and then keep waiting. Well, as soon as memory reads username and yeah, right. Zoom keeps annoying me a little bit. Anyway, so we can hijack data while they're on their way to the secure container. They can be hijacked. So how to protect yourself from this kind of attacks? Even if you have access to the regular kernel mode, and even if you implant your malicious driver there, you have access to almost any address allocated to any process, including LSASS. But like I said, we cannot gain access here, so we only hijack. Those who have worked with Mimikatz know how it works. It's not really big deal. The driver would register nicely, piece of cake. So what can we do about it? CredGuard is not guarding us again, because before the data are in the isolated part, a credential guard is not useful. So how to combat that? Initially, so CI code integrity policies were helpful. You can have in place software restriction policies or uplogger, as we called it in Windows 7. The OS would have a blacklist to block the already known malicious drivers, but this was a static approach. It was inflexible, and the time to add something into this policy, it took a while. Service packs for Windows would only get out once every 18 months or even 24 months. But not that was the most important problem. The most important problem is that if the adversary has access to KM, if we put the control right here, then the adversary would have access to structural data that explain, that describe this CI thing. So it can change the parameters or switch those off. So this software approach to code integrity and security of the environment is ineffective. Hopefully, I drove this home for you. So what is the approach that we should use? We should use a hybrid approach where we partially use hardware mechanisms to isolate the critical components of OS from the base components with base level of a security that's easy to compromise. And this is done through HVCI, Hyper-V Code Integrity, a component that also contains CI policy. And what happens now, all the drivers that are launched in standard kernel mode have to be necessarily checked by HVCI policy. So now, in order to compromise this component here, HVCI, you have to compromise Hyper-V, the hypervisor, or to hack secure buffer. I'm drawing it here, but the secure buffer is something that's controlled by hypervisor. Address marshalling and de facto isolation of these segments from each other is performed through address translation and slap. So OS components using a SLAT as a critically important embedded part of processes can hide away HVCI, secure call, and LSA ISO into something that is inaccessible to the regular user mode and the regular kernel mode. So here, if we only switch on the whitelist, something is going wrong with video and probably my audio. Oh, okay. Whew. Great. Right, so much for that, because we need to go forward. Let me return to my slides here. How do I do that? Just a second. I just didn't want to. I just wanted to save time. You already know what VBS is. When you use hypervisors to create a smallish virtual machine and to carry out total control of access to memory by dedicating isolated containers for critically important parts of the data. Like I said, 2 instances of our OS, and all the interaction happens through the hardware component, through Hyper-V. And on software level, it's realized through a specialized security buffer. I also referred to you about. This way, we can block some of attacks aimed at compromising credentials of domain users in Windows OS. Credential Guard is a trustlet. I didn't mention trustlet, did I? OS components that find themselves in the isolated user mode are called trustlets. If you're acquainted with Intel realization, it's called enclave there. Trustlet is your enclave. It's almost, well, it's not the same, it's just very similar. Apart from Credential Guard, there are other trustlets, like virtualized TPM module, a cool thing that allows to make use of virtual TPM component that also is isolated for security purposes. It's only executed in the isolated address range. What else can be a trustlet? HVCI, the thing that I just told you about, that is in charge of checking code integrity in the regular kernel mode, that prevents launching the malicious drivers in the regular kernel mode. Right. Okay. Difference in architecture between LSS with and without Credential Guards. Everything is clear. We have our isolated element and the most critical components, the ones that realize SSP for anti-LAM and Kerberos, are situated in an isolated local security authority, and you only have to go through RPC, through a hypervisor controlled secure buffer. We also talked of Hyper-V that allows to control attack surface from malware being injected, downloaded. Okay, so we stopped attackers here in these 2 scenarios. Obviously, this is not the end. Attack surface is larger for our modern OS because we have great amounts of codes, and the greater the amount of codes, the greater the number of potential vulnerabilities, right? So let me get back to the whiteboard, and let me delete everything and write it back. So we have our user mode, isolated user mode, kernel mode, secure kernel mode. Oh, and by the way, while I'm doing it, in 12 minutes, we're going to go for a Q&A session. So you can use this opportunity to start posing me questions in the chat. Right, so kernel mode, secure kernel mode. Right, so where our adversary may want to go. Here, access is controlled with Hyper-V. So between the virtual trust level 0 and virtual trust level 1, this isolation is realized through Hyper-V, through hardware means. It controls access to data or the executed code situated on this or that virtual address. So we blocked this opportunity, right, with the malicious driver. But apart from accessing memory from our CPU, we have here our CPU, right? We also have devices that can address the memory directly because they are switched to the buses that architecturally have direct access to memory. We just looked at how to control and block attacks along these lines, along this threat vector, CPU memory access. Here, rather than registering the driver that hijacks data before it finds the data find themselves into, let's say, ISO, we can get either a manipulated driver, the driver that has vulnerabilities that can be used when used by executing user-defined code in kernel mode rather than the regular code, and thus get access to critically important areas of the memory. This DLL here is device driver. So what this DLL allows us to do, this is our memory, isolated and non-isolated. So in our regular mode, when we go through CPU, it's done by memory manager in Hyper-V, right? Between those two isolated containers, I mean. And we also have peripherals that get tied to the bus, like our NIC or our GDI, a device that's switched to us through GDI. So all of them are managed through the driver, and the adversary can potentially send instructions to access memory through the driver-controlled device. So it bypasses hypervisor, so the policy protection that we have in place is not working, right? So what to do with it? At this point of time, we don't have the necessary isolation, this one. Like this interface here, the device switched right here can address this or that. This isolation is not realized. We still have one address space, and through direct memory access, you get access to any part of the memory and dump data. So security guard doesn't help. What do we do about it? In order to cope with that, we would want to use hybrid approach. We would embed hardware support into our OS to control exchange of data through the bus, the Thunderbirds and the devices that could potentially have direct, uncontrolled memory access. This is realized through input-output memory management unit, IOMMU. Input-output memory management unit is a hardware element, and it's done by the vendor of hardware equipment. So our Hyper-V is between the software and hardware level, and we integrate those two things. So HVCI and things that we identified thanks to Hyper-V becomes applicable for devices as well. And now any attempt to access memory through that device, they go through the rules for memory access identified in Hyper-V, and if adversary tries to gain access to the regular memory space, this regular user mode and regular kernel mode, and this would be secure kernel mode and isolated user mode. So the adversary would have access right here, but not here, thanks to IOMMU. This is how we combat attacks based on DMA direct memory access. What's next? Well, actually, nothing. Hopefully you understand the general idea. Most importantly, you need to understand how virtual-based security works. Most importantly, you need to remember that all isolation is based on hardware address translation, and it's done on the guest level and between the host and guest level. Thanks to this mechanism, we provide for hardware isolation of critically important parts of service from the easily compromisable one. And one other thing that I want to end with, I mean, I have more content in my presentation, but I think you can easily download this presentation and study it on your own, because it's not an easy thing, and it's best to explain the most important elements. We are now building the foundation so that you can add the building on top of it. So for those of you who are really curious and you're really attentive, I'm giving you a practical assignment. It's okay if I draw in red, right? You're okay with that. So we have this process. We have two processes working in isolated environments. So we also have this one would be process 1, process 2, and we have address translation. So if we place it in the address 13,000 and this one in 14,000, no, these ones are guests, and then they're translated to different physical addresses, 9,000 and 10,000, right? This would be logical. Okay, now try to think it over and tell me, why would processes situated in isolated segments, or rather, no, why would processes, two separate processes, even though they use various different virtual addresses, why would they translate into the same addresses, 15,000 and 15,000? Do we have questions? If you don't have questions, then I'll spend some time explaining this assignment and yet another topic in the slide. So do we have any questions? We do have questions, Artem, not too many, but we do have some. One of the user asks, where this, in which Windows OS systems this is available, and how about secure code? What do you mean by secure code? Secure core, core, C-O-R-E. Yeah, let me answer this one first. This technology is available since Windows Pro. Even if you have OEM device with Windows 10 Pro embedded, then it's there. But once again, it's not just about software support. And the later the later your device was assembled, the greater amount of hardware protection. But if you buy a relatively old device without hardware support, even when you update your OS to Windows 10 and you use the latest edition, 20H2, you definitely are not getting the opportunity to switch those hardware and software things on. Answering the question of secure core. A couple of words about secure launch. Secure launch is technology to extend technology of code integrity into OS download technology. Attackers are now more focused not on application level and not on system services of OS, not on that level, to the firmware layer. They're going closer to the hardware because potentially it can give them greater benefits. So before secure components are downloaded, if the adversary gets access to this code, and this is called bootkit or previously called rootkit, then the adversary may get a chance to manipulate any component of OS security. Theoretically, parameters could be manipulated by adversary if the system is attacked on the system of on the stage of system being downloaded, when all our mechanisms have not yet been launched. So secure launch is a system guard kind of thing. It controls download through two technologies, the static RTM, root of trust measurement, and the dynamic RTM, DRTM. I cannot go deeper into it. You also want to bear in mind that you need to protect SMM components. What SMM is, it's system management mode, the mode in which code works with the maximum privilege level, even higher than the Hyper-V. So if if adversary hijacks our control on this level, he can bypass everything that I mentioned earlier. I do recommend you to download the slides and get to know all the details. We have AMD SMM Supervisor and Intel Shield, Intel Hardware Shield, and you have detailed explanation here what they do on each stage. Secure Core PC. In order to get all the cool stuff that I was telling you about and even more, the easiest way is to acquire secure Core PC device. Microsoft, within the framework of his partnership agreement with processor manufacturers, AMD, Intel, and Qualcomm, as well as business device manufacturers, because secure Core PC target audience are those working with really critical data, critical for the business. So what you get really secure system out of the box. I mean, Windows 10 with the firmware checked by Microsoft. The partners, Microsoft's partners, provides you with a template firmware code checked by us, and then the OEM partner builds everything on the basis of it. So what it includes is the use of hybrid approach, using software and hardware security mechanisms, including the ones that I enumerated right now, necessarily control of downloading operating system, blocking malware launched within the procedure or that tries to persist on the firmware, code integrity both in user mode and kernel mode. Most importantly, secure code PC is always on, and highly advanced protection of authentication, passwordless authentication using PIN code or biometric identification without password transferred in any way, encrypted or open. In Windows Hello, passwords are not used. These are examples. These are the notebooks, mobile devices that are included into Windows 10 Secure Code PC. All technologies are supported there, and they are by default installed and switched on, including Secured Core PC. Our target audience is composed of technical specialists. If I cannot buy a high-end business notebook, what do I do? Just give me 1 minute to show you this one last slide. Can you do it on your own? DIY Secured Core PC. Secured Code Core PC is something where you switch on all the state-of-the-art security systems. So what you see here is the list. Hardware mechanisms such as TPM module, Trusted Platform Module version 2, dynamic root of trust for measurement. This is to measure it, right? DRTM. Then isolation provided to you in system management moment, secure boot control through extension of measured boot and trusted boot. Kernel DMA is something that we draw to support memory access protection. Also, perform hypervisor code integrity to enable kernel protection, to go away from using passwords, the unsolvable security problem. This type of verifiers cannot possibly be used without vulnerabilities, and standard things like BitLockers using TPMs to store cryptographic material. You have this list on our website, and you could launch it, everything. That would be all. Thank you very much. I answered 2 questions, right? Right. Great, great. The rest of the questions will be addressed to your email address. And where can you download this presentation? Are you going to give us the link? Here is my Twitter. You can use it. I have my next presentation later today, so I'm going to publish the link to OneDrive, and this way you'll have a chance to have a look at all the slides. And I think it would be more than enough for you. Oh, and the very last thing, to look at our bug bounty program. I have bug bounty presentation today, and if you find vulnerability in the hardware and software security mechanisms that I described to you today, send it to us and tell us of our vulnerabilities. There is a separate bug bounty related to Windows 10, so let's help each other. And let's help all the users to make their systems more secure. Don't forget, security is in your hand. Thank you, Artem, and all the very best. And we are going to have a Microsoft Q&A session at 5, so We have a whole hour to answer all your questions if you like. So we can get back to this presentation. It's at 5.